In this video, I want to talk about a process called parameterizing a curve. Parameterizing a curve is the process of taking a curve and finding a vector-valued function that represents it. So it's basically the opposite of the work we did in this vector-valued functions lesson. In this vector-valued functions lesson, I gave you a vector-valued function, and I asked you to generate the curve, generate the corresponding path. What we're going to do here is the exact opposite. I'm going to give us a path, I'm going to give us a curve, I'm going to give us a line or line segment, and we're going to have to find the vector-valued function that corresponds to that. And this is going to be a skill that you use quite often, particularly if you're planning to take Calculus 4. Now, parameterizing any and every curve is a very difficult and challenging problem, far beyond the scope of this class. If you want to learn how to take an arbitrary curve and represent that using a vector valued function, that's the kind of thing that's taught in a computer graphics class, an advanced computer graphics class. Because, for example, that's the kind of thing that you have to figure out if you're making an art program like Paint, Illustrator, Krita, SolidWorks, or Blender. So we're definitely not going to be learning how to parameterize any arbitrary curve, but we will be learning how to parameterize the most common types of curves, specifically those types that tend to arise in Calculus 4. And to begin with, let's talk about how to parameterize lines. Now, in order to parameterize a line, you need two pieces of information about that line. The first piece of information that you need about the line is the line's position in space. Where is the line located? And to that end, what you need is one point on the line. If you know one point on the line, then you can create a vector R0 that is pointing to that one known location that's on your line. So this is one piece of information that you need in order to parameterize the line correctly. You also need to know how that line is tilted, slanted, oriented in space. So you're going to need what we call a direction vector for the line. A vector that points in the same direction the line is pointing. So for example, if you've got a two-dimensional line, a line in two-dimensional space, and the line that you're trying to parameterize looks like this, you're going to need to know two pieces of information about this line. The first thing that you're going to need to know is a single point that's on this line for sure. And you're going to need to create a vector r sub 0, which points to that known location on the line in 2D space. Then you're going to need to know one vector that tells you how the line is tilted or oriented, and that's the direction vector d. The direction vector is a vector that points in the same direction as the line. So this would be a picture of the two pieces of data that you need to know about this line in order to be able to parameterize the line. Once you have those two pieces of data, you can parameterize the line using the following formula. R of t is equal to the direction vector d scaled by the amount of time that's passed, scaled by t, and then add the position vector in the back, direction vector times t plus position. direction vector times t plus position. A word on why this formula works. This formula works because of triangle rule. Let me go ahead and recreate this picture in GeoGebra so that we can see how this formula points to every location on the line as t takes on every possible value. So this red vector R0 is pointing to our initial known location on the line. And then this blue vector is a direction vector for the line. And when we multiply that direction vector by t, what we're doing is scaling that direction vector. So by multiplying by different values of t, we can either extend that direction vector and make it longer, or we can shrink that direction vector and make it shorter, or if the t's are negative, we can actually flip that direction vector and go backwards along the line. So then when we add together the direction vector times time plus R0, what's happening is basically triangle rule. We are going along R0 to this intermediate point on the line, then we're following the direction vector, and the sum of those two quantities is pointing directly from the origin to this other point here on the line. So this black vector extending out from the origin are the outputs of the function r of t that has been created according to this formula. And so as we vary the values of t and extend and stretch that direction vector in various ways, we are getting an r of t that is pointing from the origin to these different locations on the line. And so that's why this formula works to parameterize this line. So let's go ahead and use this template to parameterize the line with the following data. This line has a direction vector d equals 3, 1, 2, and it also passes through the point 4, 1, minus 3. So let's parameterize this line. Let us find a vector valued function which represents this line. Pretty simple question because we're directly given the information that we need to fill in the template. We're directly given the direction vector d, 3, 1, 2. I'll scale that by the t value, and then I'll add in the vector pointing to this known location on the line, 4, 1, minus 3. So this would be my final answer. You could simplify this if you wanted to, but it's not necessary. Here's a slightly more interesting variation of this problem. We have a line that's passing through two known points. Let's go ahead and parameterize this line. To help me conceptualize this problem, let me go ahead and throw down a quick sketch. Let's imagine that this is the line that's being discussed, and I have a point here, 7, 1, minus 5, and I have a point here, 1, 0, 3. Now, I could use either of these points as the r subscript 0 in my formula, but what I currently lack is information about a direction vector for the line. So do you have any ideas about how we might find the direction vector from these 2 points? Well, I think a direction vector that would work is the displacement from one point to another. The displacement vector between these points lies in the same direction as the line, so it will serve as our direction vector d. So let's subtract these points. For example, I could subtract them in the order 1, 0, 3 minus 7, 1, negative 5. And I would get the direction vector 1 minus 7, 0 minus 1, 3 minus negative 5, which simplifies to negative 6, negative 1, and 8. Now, just as a remark, it would also be correct to subtract the points in the opposite order. What you would get if you subtracted the points in the opposite order is just the direction vector pointing in the opposite direction. But that's okay as long as the direction vector lies parallel to the line. As long as the direction vector lies parallel to the line, it doesn't matter how long the vector is, and it doesn't matter whether it's pointing forward or backward, because eventually, as t runs through all of its possible values, the function will reach every single point on the line, no matter what. So now that I have this direction vector d, I can choose again whichever one of these 2 points I want for my r sub 0 for the line. I might choose this one, 1, 0, 3, just for convenience. So with that said, the parameterization for my line, which I'll call L of t, L for line, is -6, -1, 8, scaled by the parameter t, and then plus the point 1, 0, 3 in the back, converted to a vector. So this is the process of parameterizing a line. If you want to find a vector valued function that represents a line in 2 or 3-dimensional space, all you need to do is find two pieces of information about that line: a point on the line and a direction vector for the line. If you can find that information from whatever data you're given about your object, you can use that template d times t plus r naught to parameterize the line. Having talked about parameterizing lines, let's now talk about parameterizing circles. And we can take some inspiration from the parameterized circles that we encountered in our vector valued functions lesson, as well as from the associated problem set. If we want an object to move in a circle, we can accomplish that by using the functions cosine and sine for the x component and for the y component. And if in particular we want the radius of the circle to be r, we can accomplish that by scaling those functions by r times cosine of t, r times sine of t. Now, just as in the vector valued functions lesson, this function will cause the circle to be traversed in the standard direction, counterclockwise movement over time. If you want to move clockwise around the circle over time, all you have to do is plug in an extra minus sign to the input of sine and cos. And you would have explored this in the problem set on the vector valued functions lesson, that by putting minus t in sine and cosine, this causes the circle to be traversed backward because the angles are being flipped before they're getting plugged into sine and cosine. Quick example, just to reify this formula before we move on. If someone asked us to parameterize a circle radius 5, then we would say, okay, circle radius 5 traversed counterclockwise would be 5 times cosine of t, 5 times sine of t in the clockwise direction. We would just put a minus t in the input instead of positive t to cause the angles going into sine and cosine to be drawn clockwise. Now, if you don't want a full circle, if you only want a portion of a circle, like a quarter circle or a semicircle, that can be accomplished by putting a restriction on the values of t going into this function. If we wanted to parameterize an upper semicircle of radius 7, we would start out with the formula for the full circle of radius 7, 7 cosine t, 7 sine t, but then we would restrict the values of t going into sine and cosine so that only the upper semicircle is produced. Now, if I think about this function, the values of t are serving as the angles going into sine and cosine, and the upper semicircle corresponds to angles that are between 0 and pi radians. So the domain restriction for the upper semicircle would be t values in the interval from 0 to pi radians. Similarly, if I wanted a right semicircle of radius 7, a right semicircle, so this portion over here on the right side of the xy plane, These correspond to angles within a certain interval, angles between a value of, I could say, negative pi over 2 going up to positive pi over 2. Then as t increases from the angle negative 90 degrees to the angle positive 90 degrees, as t increases from this lower value to this higher value, I'm generating every single point on this right half of the semicircle. So my parameterization for this shape would just be 7 cosine of t, 7 sine of t for t's between negative pi over 2 and pi over 2 radians. Now, one of the questions that I get from students in this section is, what if you want your circle to be positioned somewhere other than the origin? Because all the circles that we have created so far are centered at the origin. If you want to move your circle someplace else and displace it away from the origin, you can just do that using vector addition. So if you want to move your circle, for example, over here to a point x naught, y naught, then you start by putting in a vector that points to that location. And then from that point, you move to points on whatever circle it is you're trying to generate. So this action of first following the pink vector and then following the blue vector to reach a point on this circle, that action is exactly what vector addition allows you to do. So you could do something like r of t equals whatever is your radius cosine, radius sine, and then add in a vector x0, y0, which points you to your displaced center. Finally, let's talk about how to parameterize curves that are obtained by graphing old school algebra functions y equals f of x. For example, how to parameterize this cubic curve y equals x cubed minus 2x plus 1. The advantage of taking a curve like this and parameterizing it is that it unlocks some special abilities involving calculus of vector valued functions, which we will study over the next several lessons. The easiest way is to just make a decision up front. In my parameterization, I'm going to set the x equal to t. And that decision is reflected by putting t in the x component of the parameterization. Once you have made the decision that x is going to be equal to t, you just have to make the corresponding change in the formula for y and replace y with, instead of f of x, f of t. So for a quick example here, returning to that cubic curve, if I want to take the cubic curve x cubed minus 2x plus 1 and express it as a vector valued function instead, all I have to do is decide up front that x and t are going to be equal, and then force the y formula to match that. So t cubed minus 2t plus 1. It is possible to make other decisions giving you other valid parameterizations of this curve. Something that you'll see in certain contexts is to make a decision like, I'm going to replace x with t squared. And if I say that x is equal to t squared, what that means is that x cubed becomes t squared cubed minus 2x becomes t squared plus 1. Or you could replace x with something else, like, sometimes see x replaced with sine of t. Then what would happen in the y position is that you just have to replace x with that quantity, sine of t cubed minus 2 times sine of t plus 1. It changes the sort of rate and the pace at which the curve is traversed over time. If you set x equal to t, then you'll be traversing your curve from left to right. at a constant horizontal speed. But if you replace, by contrast, x with something like t squared, what you're going to see is that the curve is traversed slowly in the beginning, then faster over time. So here's a quick demonstration of that principle on GeoGebra. Here in blue is the cubic curve that I'm trying to parameterize. And the vector v is the vector that's being produced by this first parameterization t, comma, t cubed minus 2t plus 1. And so let's see how this vector changes over time and points to different locations along this cubic curve. For example, this is where we're pointing when t is equal to 0, and let's increase the values from there and play this function. So you can see it's traversing the curve at a relatively stable and constant rate. But by contrast, if I parameterize the curve using this function where x is equal to t squared, let's look at how this function points to different locations on the curve over time. In the beginning, it moves very slowly, and then off it goes. And it begins to accelerate and move faster and faster as time goes along. So by replacing x with other functions, you can cause the graph to be traversed at different speeds. And we'll talk more about that in the next lesson when we discuss interpolation. That concludes this lesson. Today we learned how to parameterize common curves. If you're parameterizing a line, then all you need to know is a direction vector for the line and one point on the line, data about the line's position and about the line's slant. If you have that data, then you can parameterize the line using the formula direction vector scaled by t plus r sub 0. If you want to parameterize a circle of radius r centered at the origin, you can use the formula r times cosine of t, r times sine of t. And then if you need to parameterize other circles or other portions of circles, you can do that by just manipulating this basic template in various ways. For example, if you need to traverse the circle specifically clockwise over time instead of counterclockwise, then you can do that by making the t's negative and applying a minus sign to those inputs. If you need to parameterize a portion of a circle, you can do that by imposing a domain restriction and restricting the values of t that you plug into your parameterization. If you need to displace or move your curve to another center instead of the origin, you can do that just by adding a vector to your parameterization to displace the circle out to that position. Finally, we learned how to parameterize basic algebra functions, y equals f of x. One surefire way to do that is to just set x equals t and then make the y of t function change to match that. Instead of y equals f of x, change it to y equals f of t. And this parameterization will point to different locations along the curve over time. And as time increases, you'll be traversing the curve from left to right at a constant horizontal speed. If by chance you needed to traverse your curve differently, for example, you needed to traverse your curve slowly at the start and then faster over time, you can accomplish that by replacing x with other functions. For example, you could replace x with t squared. And then all you would have to do is make the corresponding change in the y component to match that choice.